Okay, all right. So it is Friday of week 2. Um, yeah, if it weren't for these classes, I feel like I would lose track of all time here. But here we are. It's Friday of week 2, and the topic for today is regularization. Okay, so regularization. These are also called shrinkage methods. Um, and they're methods to kind of adjust the coefficients that we fit. Okay, all right. So it's a way to address overfitting, right? So in machine learning problems, we commonly run into the problem of overfitting our data. And what overfitting means is that the model that we fit ends up modeling odd specifics of our training data, right? We can predict the training data very well, but we cannot predict new data very well, okay? And we saw that on the cross-validation, in the cross-validation lecture when we fit the 17th order polynomial. It was very, very wiggly. It fit some of the data points very well, and that the training, the data in the training set had very, very little error. But because it was so wiggly, when new data came in, it did a very poor job of fitting those things, right? So cross-validation is a tool that we have to avoid selecting a model that overfits the data. And the way cross-validation works is that it splits our available data into a training and a validation set. And that's how and it uses the validation set to measure the model's ability to make predictions, okay? And so the model's performance is not based on just how it performs in predicting the training data, which is what it was using to get its parameters, but it's measured on how well it predicts data that was not part of the training process, and that's an important part. And so cross-validation is a very widely and frequently used tool. Today, we're going to talk about regularization. Regularization is another method that we can use to avoid overfitting. And the way regularization works is that it modifies the loss function itself to penalize complex models, okay? So right now, the loss function that we've been using has been the ordinary least squares, or the least squares loss function, or the mean squared error loss function, okay? And basically it's saying, the way we pick our W's, is that we want to minimize this loss function, right? So we treat the T and the X as fixed values, and we are picking the W, okay? The weights, the coefficients in our model, so that this loss function is as small as possible. That's what we're doing so far, okay? And that's how we say, well, this is the best model, okay? But one problem with this, is this related to BIC? There's certain concepts that are similar to this in BIC, except AIC and BIC are measures that we use after the fact, okay? They come after the fact. You fit the model, you fit the least squares model, and so your coefficients are guided by least squares, but then you have two models, one, this least squares model and this least squares model, and you're using the AIC and BIC after the fact. We are modifying the loss function itself, and we are picking the coefficients that do not minimize the least squares loss function, but a modified loss function, okay? And the idea here is that if we're guided only by mean squared error, this loss function, is that we can end up picking an overly complex model, because generally, the more complicated model you have, you're going to have a lower MSE, right? You're going to have a lower loss function. And so, so what we do here is we actually change the loss function itself, okay? So this is not a measure at the that we use after the fact, but we use it during the optimization process itself. We are trying to find the W's that will minimize this. This is a modified version of the loss function, okay? And so we call this L prime, okay? This is the regularized loss, okay? And what it is we take the loss function. So the loss function, the ordinary least squares loss function, is part of L prime, but we're also adding on a complexity factor, okay? So if your model gets more complex, then L prime is going to go up, okay? So you can keep changing your W's, make your model more and more complicated, which will reduce this ordinary least squares loss, but it comes at the cost of adding more complexity. And so when you add the complexity and the lambda together, or not the lambda, and the loss together, you get L prime, the regularized loss. And we want to minimize the regularized loss. So we're not just minimizing the OLS, but we're also, we're still trying to shrink this, but it's balanced out by a complexity factor, okay? And the complexity factor is multiplied by some weight lambda, and the lambda is how much the complexity is penalized. Okay. So so let me make an analogy. Okay. So so we do, you know, sort of similar things in that we might have two goals. We want to, so here we've got two goals that we're trying to handle, right? We're trying to reduce complexity and we're trying to reduce OLS, right? And if we were only guided by OLS, we would pick a super complex model because that would reduce OLS. But we know that's not the case. We want to keep the complexity down as well. So here's a, you know, an analogy from real life, right? So one day maybe you have to search for a place to live, right? And let's say you're considering two different apartments, and I just made up some numbers, okay? And so let's say one apartment costs $2,000 a month, okay? But the commute to work is only 10 minutes each way. The other apartment costs $1,700 a month, so $300 a month less, but the commute is 40 minutes each way, right? So so which apartment do you pick, right? The $1,700 a month, that's going to cost you an extra hour a day in terms of commute time, and the question is that worth an extra saving $300 a month, right? So, you know, if money is the only factor that matters, then it's easy, right? You just pick the apartment with the lowest cost, okay? You pick the apartment with the lowest cost. But, you know, most people value their time to some degree, and the apartment with lower rent comes with a penalty in that you have to spend more time, basically an extra hour a day on the commute. This is 20 minutes commuting each day. This is an hour 20 commuting, right? So you're spending an extra hour. So the question comes down to is how much you value your time, right? So let's say you have an active social life outside of work, or you really hate commuting. In that case, the penalty of having the longer commute is going to be heavier, and you'd probably select the apartment that's closer to work. The penalty, meaning that the penalty of commuting outweighs the savings on rent, okay? On the other hand, if you don't do much with your time outside of work, okay, or you don't mind the commute, let's say you enjoy listening to podcasts and audiobooks and whatnot, then the penalty for having a longer commute is greatly reduced, and you probably select the apartment with the lower rent, and you'd say, with that extra cash, I can do something nice, right? So the true cost of the apartment is the rent, okay, plus some preference factor times the commute penalty, okay? And these are kind of the same pieces that go into the regularized loss. So regularized loss would be this part, kind of the loss, and it's equal to the ordinary least squares loss plus lambda times a complexity parameter, right? So we want to reduce complexity and keep our loss function small, our you know, sum of squared losses small. And which one's more important is guided by this preference factor. Right. Okay, is that okay? If we're following me, just give me some feedback, give me a green check, let me know that we're good. If you got questions, please indicate so as well. Okay. Most of you seem to be okay. No one's given me, so far everyone's giving me green checks, so that's good. All right, great, thank you for your feedback. Okay, so the key thing to keep in mind is that we are still optimizing a loss function, okay? So, so this is, the apartment analogy is not perfect in that we're not comparing one model directly with another, okay? We're not comparing two models directly. What we're doing is that we have modified the loss function and we are still trying to optimize the loss function, okay? And so the coefficients that we are going to use are the ones that minimize this modified loss function. So, so this is what we're going to use. Okay, so we've modified the ordinary least squares loss, which is just regular old L. Okay, by adding on lambda times some complexity factor. Okay, and complexity, which we might more generally write R of F. Okay, and this is kind of the regularization factor for some function F. Okay, and this is going to be our regularized least squares loss function. Okay, because we take the ordinary least squares loss function and we're adding on this complexity, right? And you can read more about it on Wikipedia. And so the question is, how do we measure a model's complexity? How do we measure a model's complexity, right? All right, and so just imagine two possible models. One, model A fits a fourth order polynomial, and model B fits a fifth order polynomial, okay? And from this, we know that the fifth order polynomial is more complex, okay? The fifth order polynomial, this is what it would fit, okay? W0 plus W1, W2, W2x2 xn squared, W3 xn cubed, W4 xn to the fourth, and W5 xn to the fifth, okay? If you force W5 equal to 0, okay, if you force this coefficient equal to 0, then this thing, okay, is equivalent to the to a fourth order polynomial. Sorry, I have these subscripts wrong, okay? So reducing, changing W5, changing a coefficient equal to 0 reduces the complexity. It takes it from a fifth order polynomial down to a fourth order polynomial if you just reduce the size of the coefficient down to 0. So one way to measure model complexity is to just count how many coefficients we have that are not 0, okay? You count how many coefficients you have that are not 0, and that could be a measure of model complexity. If you have two coefficients that are not 0, then that would be a simpler model than having another model where there's 4 coefficients that are not 0, right? So we can just count how many non-zero coefficients we have. This is also known as the L0 norm, okay? The L0 norm. But here's the problem. If you just use the count of non-zero elements in the vector W, which is using the L0 norm, okay, which is written this way. So a little bit of your linear algebra stuff. It turns out it's really difficult to optimize, okay? The loss function in this case is what we say is not convex, okay? And you end up having to consider all the possible permutations of which elements in W are not 0. And when they are not 0, when they're non-zero, what value they should be, okay? And so if you've got a model with any more than a few terms, the number of calculations that you have to run through to try to optimize this just becomes staggering and almost really, really hard to do, okay? And so you can try, you can read about this on Wikipedia. There's a special segment in the Regularized least squares article talking about using the L0 norm, and it's really hard to do, okay? So, so instead of using the L0 norm, we can use the L1 or the L2 norm, okay? The L1 norm is known as the Lasso, and it's the absolute value penalty, okay? So instead of just counting which elements are non-zero, what we can do instead is we can just add the absolute values of the elements in W, okay? So instead of saying, okay, you know, this one's not zero, it's got some number on it, okay? It's got a number associated with it. And so we're just gonna add the absolute values, okay, of all of our weights together, all right? And that could serve as a measure of complexity in the model, right? So we would say, so non-zero values of W, okay, will contribute to the penalty factor. Larger values will end up contributing more to the penalty factor. And if a coefficient is zero, then the variable is not counted and does not contribute to the penalty factor. And so, so when we are trying to modify or minimize this regularized loss function, then you know, picking a different coefficient for W might reduce the loss function, the ordinary least squares loss function. But if it means increasing W, okay, it has to be you know, the amount you increase W by has to be greater than I mean, cannot be more than how much the OLS loss goes down, right? So it's kind of, just imagine having these knobs that you're turning and you're trying to reduce the ordinary least squares, but if it means pushing W up so it gets bigger, then that's going to change the complexity, right? So that's what we have. So this is called Lasso. This is called Lasso. We can also use the L2 norm, okay, which is going to be the sum of the squared values and the elements of W. So you take this vector W, kind of your vector of coefficients, all right, and what you can do is you can square each of the elements and add them all together, okay, and this has the effect where the larger values of W are more heavily penalized, okay? And smaller values of W, okay, values less than 1, are still count as part of your complexity factor, and it's penalized, but much less so, right? Once you go below 1 and you square it, it actually gets even smaller, right? So this is known as ridge regression, okay? And one effect is that ridge regression favors or prefers when the values in W of your coefficients are similar in size to each other. So it favors when the W's are, you know, smaller and similar in size to each other. So that's these are some options here. Okay. How do we feel about this? Is this okay so far? All right. Okay. All right. Okay. Well, thank you for your feedback here. One objection that that students or people may have as I introduce this, though, is that how does the size of a coefficient measure complexity? Okay. So so back here, a lot of people usually have no problem saying that, okay, we're going to count how many non-zero coefficients there are, and the more non-zero coefficients you have, the more complex the model you have. That seems to make sense to a lot of students. Okay, but then the idea that the size of the coefficient measures model complexity, sometimes I give students have a hard time handling that. Okay, because if you think about it, if two models have the same number of variables, right? Let's say this model uses 4 variables and this model also uses 4 variables. Aren't they equally complex, right? So that's a question, right? And you know, why would one model be more complex? So let's say this has 4 variables and this one has 4 variables, and this one just has bigger coefficients. Why is the one with bigger coefficients more complex, right? And if bigger coefficients mean more complexity, then can't we just shrink the coefficients? Or like change the unit of measure, right? Like if you go from inches to miles or miles to inches or something, or centimeters to meters or meters to centimeters, you can change the size of the unit, and that's going to change the coefficient. And won't that change your complexity? Does that make sense, right? Should changing the units change your complexity, right? And so these are valid objections, okay? And so I'm going to try to address these things, okay? And so so one is that yeah, we don't want a model. We don't want to say the complexity is based on what unit you use, right? So we don't want that, right? So if somebody uses centimeters and somebody else uses meters, the person who uses centimeters will probably have smaller coefficients, and the person who uses meters will probably have bigger coefficients. And we don't want to say just because you chose a different unit, you're going to have a more complex model, okay? So to address that, we almost always recommend that you center and standardize your variables, right? So centering means you add or subtract a constant to each column of X so that each column of X has a mean of 0, right? So that means that's centering the X values. And then standardizing means you multiply all of your values in X by some constant so that the standard deviation is 1, right? So if you got big numbers, you multiply it by a constant less than, a small number, so that after the fact, everything has a standard deviation of 1, right? Okay. And then an alternative, sometimes you have a function that doesn't allow negative numbers, okay? And so you can kind of scale everything to fit between 0 and 1. So that's another option, okay? But basically, we recommend centering and standardizing your variables. And that addresses the issue of using different constants, right? Or different units of measure. So if one person uses centimeters and one person uses meters, after you center and standardize, they're going to both be exactly the same number, okay? So that's going to address the concern of using different units, producing different coefficients and different measures of complexity, okay? Okay, so that addresses one of the concerns. But still, you might still have the question, how does the size of the coefficient measure complexity, right? Again, so, let's say there's two competing models. They both have the same input matrix X, and X has been centered and standardized, okay? And let's say both models have 4 X variables, right? And both models have the same coefficients for X1, X2, and X3. And then the only difference is that model A has a large coefficient for X4, let's say W4 is equal to 1. And model B has a tiny coefficient for X4, let's say W4 is 0.01, okay? And so with the exception of this coefficient for X4, this W4 value, model A and model B are the same, okay? And so I would argue that model B is less complex than model A, okay? And I argue that model B is less complicated than model A simply because it has a smaller coefficient for X4. Okay, simply that the only reason why model B is simpler is because W4 is a smaller number. Okay, and I don't know how you guys feel about that, but I'm going to try to make my case and saying that if you look at the values of W, that can be a measure of complexity. Okay. All right, so when that W4 is tiny, 0.01, okay, the tiny coefficient means that changes in that predictor variable, changes in X4, have little impact on the outcome variable, little impact on our prediction for the outcome variable. So if model B has a tiny coefficient for X4, then it's putting a lot less importance on the variable X4, okay? And so even though both model A and model B use that variable X4, model B is a lot closer to just ignoring X4 altogether, okay? And because it's close to ignoring X4 altogether, it's the simpler model, okay? It doesn't completely ignore it. It hasn't pushed the coefficient down to 0, but it's pretty close to ignoring it. And so I argue that that means it's simpler, right? And so here's an analog that maybe we can understand, right? So imagine there's 2 students involved in several clubs on campus, okay? And one of them, so let's say I don't know, they're both involved in like 4 clubs. I have no idea. That's like a lot, right? Okay, and let's say one one is fully invested in all of their clubs, okay? Fully invested in all of their clubs, has a busy schedule, and we would say, man, your life is busy. We can say they live a complex life, right? The other student maybe is involved in the same clubs, involved in an equal amount of clubs, but this other student is only marginally invested in each club, right? So meaning that, you know, they'll skip a meeting whenever they feel like. They don't sign up for very many responsibilities or anything like that, right? So we would say this student's involvement in each club is not zero, but it's a lot lower, okay? And I would argue that the student who's less involved, that student's life, you know, is quote unquote simpler, okay? Now, whether simpler is a good or bad thing is out, you know, not what I'm trying to say, but I'm going to say that the student who's only marginally involved in these different clubs, their life is simpler and less complex versus the one who's fully invested, okay? And so even though they're both involved in kind of the quote same amount of things, one is much more involved and then the other one is less so, okay? And so similarly, I would argue that two models can have the same number of predictor variables, but if one of them weights the predictor variables a lot lower, then I would argue that it's the less complicated model, okay? Does that feel okay? Are there any questions there? No questions? Okay, all right. Okay, so you bought my argument for regularization here. All right, so so do the other coefficients matter? Do the other coefficients matter? Yeah, so yeah, all the coefficients matter, right? This was just kind of isolating. If you have two models that are exactly the same in every other way, and the only thing is that this last coefficient is, one of them is smaller than the other, you know, we would argue that the one with the smaller coefficient is simpler. But yeah, this argument can be extended to all of the predictor variables, all of the coefficients, and just in general. And basically, it's an argument that this measure and this measure are valid ways of measuring model complexity, okay? Because these take the size of the coefficients themselves. We're not just saying, is it zero or not, but we're taking the size of the coefficient and we're adding up the absolute values for this measure of complexity. Here we're taking the size of the coefficients, we're squaring them, and we're adding them up for this measure of complexity, okay? And so this is just an argument that the size of the coefficient itself can be used to think about model complexity. Versus, you know, because in your 101A regression class, generally model complexity is just how many terms you have included, okay? Just the count of the number of predictors you have. But I'm trying to extend it and just say, you know, it's not just the count, but the size of the coefficients themselves, especially after you've centered and scaled them, okay? All right, and so here's just a silly example, okay? But I'm going to try to use this to illustrate how changing the loss function will how that will affect our coefficient estimates, okay? So here I make x1 and x2, and these are just the numbers 1 through 4. And because both of these are on the same scale, okay, like they're both the values 1 through 4, I'm not going to bother centering and scaling them, okay, because they're already on the same scale. They both have the same center and they both have the same scale, so I'm not going to bother further centering and scaling them. But in general, if you have different units of measure and different variables, you should center and scale them, okay? All right, and so here I'm going to have the true values of t, which is going to be 1.5 times x1 plus 1/2 times x2. Okay, so these are going to be the true coefficients, 1.5 and 0.5. Okay, and I'm just going to add some random noise to it. Okay, I'm going to add random noise, and here there's no intercept, and we're not going to try to fit an intercept. And so the model, the least squares model, the best ordinary least squares model, says, you know, because of the random noise, the best estimates are going to be 1.458 and 0.453. Okay, so these are the coefficients that we have estimated. These are the best fitting coefficients for ordinary least squares regression. 1.4588, 0.453397. Okay, so that's what we have. That's the least squares values. And I can also show that if I write a function, this is a function that calculates the ordinary least squares loss, which from earlier, the total sum of squares loss is t minus xw transpose times t minus xw. Okay, here's a function where I put in the observed data, okay, and I have coefficients w1 and w2, and what it will do is it makes a matrix out of w1, w2. It takes the observed first two columns of the observed data called x. It takes the third column of the observed data and calls that t, and then it calculates the loss function by doing t minus xw transpose times t minus xw. Okay, so this is just a way to calculate the loss function. And then I want to use this with that function optim. Okay, I want to use it with optim. So I hope you read the notes on how to use optim or recall from 102A. And yeah, forcing zeros to you mean back on this slide, or so this zero here just means don't fit an intercept term. Okay, yeah, don't fit an intercept term. That's all I'm doing, and because the true model has no intercept term, and so I just want to see the effects of predicting this and this. Okay, so we're not going to bother fitting an intercept term. Okay, and so anyway, here's our function that we're trying to minimize, our ordinary least squares loss. And then if I run that into optim, I can say just start at some arbitrary point 0, 0. The function that you're trying to minimize is this ordinary least squares function. Okay, and what are the values you get? Okay, optim says the value that minimizes this ordinary least squares function is going to be 1.4588, 0.4533. Okay, which is pretty much exactly what we got here. It's off by a tiny bit, but that's just because optim will stop when it gets close enough, right? So optim, it says it's reached convergence when the value it reaches is pretty much close enough to not changing anymore. Okay, so we're saying, so we're going to modify this loss function, and we're going to have optim find the values that minimize the modified loss function. Okay, so right now we asked optim, R's internal optimization function, to find the values of w that will minimize this loss function. Okay, and in order to just get it to work, I had to put in a wrapper function, right? Because optim just provides a single argument par, and our function takes in observed data w1 and w2 and stuff. Okay, is that all right? So oh, okay, and then this is just a contour plot. Okay, so so this is the ordinary least squares contour plot. Okay, this is the w1 variable, and this is the w2, and we can see this red dot represents the value that minimizes the ordinary least squares function for our observed data, and this is very close to the true value of 1.5, 0.5. It's the true the values that minimize the loss function for observed data is 1.458, 0.453. And that's this coordinate. Okay, so this represents the value that minimizes the ordinary least squares loss function. The value of the coefficient for W1 and the coefficient for W2. All right, so this is what I'm going to do. Now we're going to look at the lasso, the L1 penalty, okay? And so for the lasso loss function, okay, is going to be the value of the ordinary least squares loss function, right? So this is the ordinary least squares loss function. That's what I have right here. And to get the L1 loss, we take the ordinary least squares loss and we add lambda, just some arbitrary choice of lambda, times the L1 norm, which is going to be the sum of the absolute values of W1 and W2. So whatever W1 and W2 are, we take the absolute values of those things and we sum them up. We're going to multiply that by lambda. And this plus this together forms our L1 loss. Okay. And again, just to get it to use with Optim, I throw this inside a wrapper function. Okay. And I ask R to run Optim, okay? Starting at some arbitrary 0.00, find the values of W1 that will minimize the L1 loss, okay? So this is what we have, right? So we're trying to minimize this L1 loss function. So find the values of W1 and W2 that minimize the L1 loss, okay? Sorry, is lambda just an arbitrary constant that we decide? Yes, yes, right? So lambda is the preference factor. Which is more important, the simpler model or minimizing the least squares term, okay? And so here I've run the same thing, right? We're trying to minimize the L1 loss, but we're going to try using different values of lambda. We're going to try lambda equals 10, lambda equals 50, lambda equals 100, okay? We're going to try different values of lambda, right? And basically larger values of lambda say you are going to take that complexity model and say the penalty incurred is greater, right? And so what we see is that as lambda increases, our coefficients for x1 and x2 go down, right? x1, so if we don't have any loss function, if lambda were equal to 0, it would be equivalent to the ordinary least squares measure, and these are the values that minimize ordinary least squares. As we increase lambda, these go from 1.458 to 1.436 to 1.345 to 1.231. As I continue to increase lambda 180, it shrinks to 1.049, lambda to 300, 0.595, lambda to 500 basically takes me to 0. Okay, this is effectively 0, and this is also effectively 0. Okay. Let me just show you what this looks like, okay? The red dot represents the ordinary least squares loss, okay? And these are the contour lines of this modified loss function, okay? So the modified loss function has these contour lines. Right now, the contour lines kind of look just like the ordinary least squares loss. But as I increase the lambda, I'm gonna flip through some slides, okay? Almost like an animation. As the lambda gets bigger, the contour lines will change shape. And this blue dot represents the values that minimize the this modified loss function. The red is the value that minimizes the ordinary least squares loss function, and that will always be at this 1.5, 0.5-ish value. And then the blue dot will be the value that minimizes the regularized least squares loss, okay? And so as I increase lambda, the coefficients change, and you can see the loss function, the contours of the loss function change, okay? So let me just kind of, so lambda 10, as I increase, this is, I don't know how fast Zoom refreshes, okay? So I guess I'll flip slowly, okay? So here's lambda equals 10, lambda at 30, lambda at 50, lambda at 100, lambda at 150, lambda at 180, lambda at 200, okay? And at lambda equals 200, W2 is 0, basically, okay? And W1 is something else. Lambda at 250, lambda at 300, lambda at 370, and lambda at 500. At lambda at 500, it has pushed both coefficients down to 0 here, okay? So that's what happens. As you increase your lambda, the contours of the loss function change, okay? You no longer have these ovals. You get these kind of these weird angles going on here, okay? And what's going on there is that basically values that aren't 0 get penalized, okay? With the absolute values of the functions, anything that is not 0 is going to count as into the penalty, okay? And And that's what we have. So as the lambda increases, the contour lines begin to have sharp corners and straightish edges. That's an interesting thing, okay? And as lambda increases, we saw the optimal parameters basically travel diagonally until it hits the x-axis, and then it gets pulled towards 0. And basically what's happening with this is that the penalty from increasing one coefficient from 10 to 11 is the same amount of penalty or complexity that gets added from increasing coefficient from, say, the number 1 to 2, okay? So shrinking a coefficient from 1 to 2, or 2 to 1, or 11 to 10 gives us the kind of the same improvement here. Let's take a similar kind of look when we're looking at the L2 norm, okay, the ridge regression loss. And so again, we're taking the ordinary least squares loss and we're adding lambda times the sum of W squares. So we're going to take the W's, we're going to square them, and we're going to sum those up, okay? And we're going to try to minimize this, all right? And so this is what we see here, okay? If we had lambda equal to 0, it would start off right here, okay? But as I increase lambda from 10 to 50 to 100, we can see these values shrink, okay? And at lambda equals to 500, they've shrunk, but they're not quite at 0, okay? And so let me just show you what these pictures look like, okay? And again, here's the contours. I've added this diagonal line representing W1 equal to W2. And so when I put in lambda equals 1, the red dot represents the OLS loss, and the blue represents kind of our modified values. And so what this will do is it will push the values will approach this line, and we can see the contours also adjusting, and they shrink towards this, but you know, even at lambda equals 1,000, we don't get to 0, 0. Okay, so this is the animation that we see, okay, or the different pictures that we see. As lambda gets bigger, the contour functions become more circular, and the path of this blue dot does not follow the same path as it did for Lasso. What it does is, so with Lasso, what we saw is the blue dot first went diagonal towards this axis, and as it hit the axis, it then got pulled into 0. Here, it's going to move towards this line. Okay, it's going to move towards this line, and then it's going to get pulled down to 0. Okay, that's what we see. Okay, so what is happening there, right? So one thing to note is that the contour lines looked less elliptical and more circular. And as lambda increased, what we saw is that the parameter values tended to travel towards that line, W1 equals W2, until it got kind of close and then was pulled towards 0. Okay, so why is it doing something like that, right? It's always good to think about why. So for the ridge regression, your penalty is you take your W coefficients and you square them, right? And so the difference between W equals 10 and W equals 11, that difference goes from 100, 10 squared is 100, 11 squared is 121. So you get a difference of 21 points. Going from 1 to 2 though, okay, W1 equals 1 has a penalty, 1 squared is 1, 2 squared is 4, okay? And so going from W1 to 1 to 2 changes your complexity only by 3. Going from 1 to 4 changes your complexity by, has a change of 3. Whereas going from 10 to 11 changes it from 100 to 121 and has a, you know, so if we had to pick which values we should reduce, okay, we have a coefficient that's 2 and a coefficient that's 11, we would rather reduce the 11 down to 10 than the 2 down to 1, okay? And so L2 is going to kind of push, is going to first affect the coefficients that are bigger, like 11 or whatever, the big coefficients first, until they're all kind of fairly equal in size, and then they kind of push them down equally. Whereas with the L1 penalty, okay, when we were looking only at the absolute values, changing 11 down to 10 impacted our complexity by 1. Changing our coefficient from 2 to 1 also impacted it by 1. So if we had two coefficients, one's at 2 and one's at 11, and we say, which one should we reduce? There's no preference there. They both, reducing either of them has an equal impact. So both of them would get reduced probably by 1/2. We would push 11 down to 10.5 and 2 down to 0.5 is what would end up happening there, okay? So, why bother with the regularization? How would this help us? How would this help us avoid overfitting, okay? The reason why it would help us avoid overfitting is that what it does is it ends up reducing the amount of variation in the amount of variation in the W1 and W2 estimates, okay? So I'm going to show a bunch of dots here, okay? So what I've done is I fit 1,000 different samples based on the same model, okay? So remember, all the way back here, when I generated this data, okay? When I generated this data, I added random noise, okay? And so here, these estimates, 1.458 and 0.453, these are based on this observed data between x1, x2, and T has random noise. So if I generated a new set of data, I would get different random noise, and I would get different coefficients. Oh my gosh, I forgot about my quiz thing. Where did I put that? Okay, but I would get different random noise, and I would get different coefficients, okay? And so what I've done in these later slides is I've done 1,000 different samples of data, each with different random noise, and so we're going to get slightly different coefficient estimates, okay? And that's what these, the black dots on this first slide represent all of the different coefficients that we might get from just the different random noise, okay? And what happens is as I increase lambda for the lasso, okay, all of those coefficients kind of slide down, okay? The whole cloud of points slides down until it hits this, and as soon as it hits 0, we're not going to get better values by going into the negative side, okay? The complexity is only going to go up if we go onto the other side. And so the cloud of points crashes down, and then if we keep pushing it to lambda equals 500, they're all going to end up crashing here into this a single dot here. For the L2 penalty estimates, what we see is that the cloud of points here will get smaller and smaller and smaller. We have less and less variation in the different W1 and W2 estimates that we get. So when lambda is 500, the variation that we have in W1 and W2 is quite small, okay? But we probably wouldn't ever pick lambda equal to 500. But what we see is that the variation of the estimates, right? So how reliable is your estimate W1 and how reliable is your estimate W2 will shrink as your lambda increases. Okay, sorry. Today's quiz answers for Friday is first quiz question, C as in cat, and second quiz question, A as in apple, okay? First quiz question, C as in cat, and the second quiz question, A as in apple, all right? Any questions there? C as in cat, A as in apple for today's quiz. Okay. All right, so I'll probably expand on some of my observations here, but that's it for today's lecture. Have a good weekend, you guys, and stay safe and stay healthy out there, and we'll see you guys on Monday.
Professor, I have a general question about the concept of optimizing.